Hello everyone, my name is Felix Leditzky, and in the first part of this talk, I want to tell you about joint work with Rotem Arnon-Friedman on upper bounds on device-independent quantum key distribution rates and the revised Paris conjecture. The main topic of our work is device-independent quantum key distribution, and we are specifically looking at the role of entanglement in this task, and we want to do this using tools from information theory. Before I explain the device-independent part, I first want to talk about standard quantum key distribution, which is the task where two parties, Alice and Bob, share quantum correlations, and their goal is to use these correlations to establish a shared key in such a way that it's secure against an eavesdropper Eves who has access to part of the correlation between Alice and Bob. And quantum key distribution protocols usually consist of two stages. In the first stage, we have the data generation and parameter estimation, where Alice and Bob use their local devices to measure the quantum state that they share in order to produce the classical data. And then in a second stage, this classical data can be further processed to yield the secret key. And Eve's goal is to try to gain information about this shared key. And in these protocols, we give Alice and Bob access to a classical communication channel, but Eve hears everything that they communicate over this channel. So this is public communication. However, Eve cannot impersonate either Alice or Bob and send messages on their behalf. So the communication between Alice and Bob through this public channel is authenticated. And then the quality of a key distribution protocol is then measured by the key rate. So we imagine that we have this quantum state sigma ABE, which is a tripartite state that describes the correlations between Alice, Bob, and Eve. And then the key rate is the maximal amount of secret key that Alice and Bob can generate or establish by executing a QKD protocol on independent and identically distributed copies of the state sigma. So this is the operational definition of a key rate. And now the goal in information theory is to find bounds on this key rate in terms of entropic quantities. One side of this is to establish lower bounds on this key rate. And this we do by exhibiting explicit protocols that achieve key generation at a certain rate. And the best example of this is the family of Wombat protocols devised by David Duck and Winter that let you generate key between Alice and Bob at the rate equal to this difference of entropies here. These are two conditional entropies defined in terms of this tripartite state sigma ABE that they share. So these are explicit protocols to give us a lower bound on what is at least achievable in terms of the key rate. And then you can ask, how close are you to the optimal rate? And this is where upper bounds come in, because upper bounds give us a fundamental limitation on key distillation that applies to all possible protocols. And a useful tool to establish these upper bounds is the so-called intrinsic information, which was transferred from the classical setting to the quantum setting by Christandl et al. And it's again an entropic quantity evaluated on this tripartite state sigma ABE. And you take its conditional mutual information, whose definition you have here, and you further process Eve's part by an arbitrary quantum channel. And the smallest such quantity when processing with a quantum channel is then equal to the intrinsic information. Okay, so these are the main data for standard quantum key distribution. And now we want to go to the device-independent setting. And in a device-independent setting, we assume that Alice and Bob cannot trust their local devices anymore, which means that they are not sure what kind of measurements they implement on what kind of quantum state. And we assume in this adversarial scenario, we assume that Eve actually distributes the state and the measurements to Alice and Bob. And she chooses them in such a way that she learns the most about the secret key that they generate. So Alice and Bob do not know how the devices work. They can no longer talk about rates in terms of a single state sigma AB. All they know now is the type of correlation that they produce when they make the measurements. Okay, so these are these correlations that we denote by P. X and Y here stand for the inputs that of Alice and Bob to the measurement devices. So these kind of select measurements. And then A and B are the outcomes of these measurements. And this correlation P is the only thing that Alice and Bob have. And it's the only thing on which they can base a QPD protocol now in this device-independent setting. And the problem now is that we don't talk about a single state and measurement anymore, because there will be many states and measurements that give rise to a certain observed correlation between Alice and Bob. And so now we need to talk about a set of states and measurements, and we denote this by this capital sigma, which is a function of the correlation, and it's a collection of all states and measurements that when Alice and Bob use these measurements on these states will give rise to the correlation they observe. And so this setting is a fairly new one. We know some things about it by now. There is a certain family of explicit device-independent QPD protocols that give us lower bounds on the device-independent key rate. And so these are protocols that work with one-way communication, and there is no pre-processing involved. And then again, once you have these lower bounds and they give you a certain rate via entropic quantities, you can ask, are these rates optimal, or how close are they to optimal? And so you're again interested in deriving upper bounds on this device-independent key rate. And an important work in this direction was the work by Karol et al. From 2020, where they introduced a new quantity called the intrinsic non-locality of a correlation and established this as an upper bound on device-independent key distillation. And the goal of our work is to analyze this bound and improve on it. And we do this in the following way. We restrict to a certain class of protocols that of device-independent QKD protocols that are based on the violation of the so-called CHSH inequality. So think of this as a Bell inequality. And whenever you violate this Bell inequality, you have a truly non-local correlation, and then you can try to distill a key from this non-local correlation. And we work in the setting where Alice and Bob divide up the correlation into two parts. The first part is the so-called test rounds, where they just test the type of correlation they have in front of them. And in the case of CHSH, there are two parameters in the game that they can test. The first one is the CHSH violation, which we call S. And the second one is the quantum bit error rate Q, which is the probability of Alice and Bob not getting the same outcome on a certain measurement. And in these test rounds, they first test whether they have the correlation in front of them that they think they have, or they kind of like test how non-local is this correlation. And then the second group of settings are the so-called key generation rounds, where they designate special inputs, which we call X hat and Y hat. And those measurement outcomes are the actual data they use for the key distillation. So this is the actual classical data that is then used to further processed. And so here in these measurement patterns here, the yellow boxes correspond to these key generation rounds. So here the X hat would be 0 and the Y hat would be 2. And the advantage of defining the device-independent key rate in this way is now that the device-independent key rate is actually the infimum over all compatible states and measurements compatible with the correlation that we have of the usual key distillation rate of that state. And so this way we can actually now use the intrinsic information upper bound that is known from standard QKD. So again, the device-independent key rate is an infimum over all the standard key rates that I can obtain from states and measurements that are compatible with the correlation that I observe. And then therefore the infimum over all of these intrinsic informations is an upper bound to the device-independent key rate. And so this is slightly different from this intrinsic non-locality, where they look at kind of like all of these compatible correlations at once, and we get to choose a particular one. And this actually gives us an extra freedom now, because again, we can pick a certain state in the measurement that will yield an upper bound on the device-independent key rate. And we actually looked at the work on the lower bounds on these explicit device-independent QKD protocols. And there we have, for a specific class of protocols, there's a certain state that is known to be optimal for these device-independent protocols. So this is the work by Peroni et al. From 2009. And our insight was that this state is optimal for the lower bound. These are optimal states for these particular protocols. And so we use them to try to get a good upper bound from these states. And it turns out that this is actually a very competitive upper bound. And so evaluating the intrinsic information of this particular state and measurement, we can do this for every value of the CHSH violation S and the quantum bit error rate Q, and then therefore get in the SQ plane our upper bound, which is the surface plot here. And you see that if I have maximal CHSH validation, 2.8 something, and 0 quantum bit error rate, I actually have an ideal protocol where I can generate a secret key at a rate of 1. But once my CHSH validation goes down or the quantum bit error rate increases, the protocols get worse and worse and the key rate decreases. And our upper bound reflects this. And it reaches 0 when you have 0 violation, because then you don't actually have any null locality anymore. And I've also marked here a specific line in the SQ plane, which corresponds to a fixed relationship between S and Q. And this relationship I've displayed here. And so this is a relationship that comes about in a realistic implementation of this protocol. And we checked our bound along this black line here and compared it to the lower bound that is known for these device-independent QKD protocols and the upper bound from the intrinsic non-locality. And so here you see on the right-hand side in this plot, the red curve is this lower bound. So this is an achievable device-independent QKD rate. The old upper bound given by the intrinsic non-locality by Karol et al. Is this yellow line here. And then our new upper bound, the blue line, significantly improves on this upper bound. And you see that for large violations of the CHSH inequality, our upper bound is actually very tight because it's very close to the lower bound. So in this regime, we actually have a very good idea of the optimal device-independent QKD rate. Okay, that was the first part on upper bounds on CHSH-based device-independent QKD protocols. And now we want to get a little more general and study the role of entanglement in device-independent QKD. And the starting point for this is the so-called Paris conjecture, which is a conjecture that Paris made in the late 90s, where he said that any state that is non-local should also be distillable, which means that you can distill the state to pure entanglement. And actually vice versa, whenever a state is distillable, it's also non-local. So the two things should be equivalent. And as a consequence of this conjecture, if it were true, is that bound entangled states, which are states that are entangled but undistillable, can never violate a Bell inequality. And then interestingly, this conjecture was actually disproven by Vertesi and Brunner 15 years later. So they found an explicit example of a bound entangled state together with some measurements and a Bell inequality, and that Bell inequality was then violated by this bound entangled states and these measurements. And what's more, not only does that bound entangled state violate a Bell inequality, but you can actually use it to produce randomness in a device-independent setting. And so therefore, these bound entangled states are actually a useful resource in a certain aspect for device-independent cryptography. And that led us to conjecture now the following fact, and we call this the revised Paris conjecture, that bound entangled states can actually not be used to generate a key using a device-independent QKD protocol. Okay, so generating a key is strictly harder than generating randomness. So therefore, this revised conjecture does not stand at odds with the counterexample found by Vertesi and Brunner. And the second thing is that if this conjecture holds, and we believe it does hold, then this will give us a fundamental distinction between QKD and device-independent QKD, because it is known that bound entangled states can be used to generate key with standard QKD protocols, device-dependent QKD protocols. And we think that this conjecture holds, and these bound entangled states, while they can be used in QKD to get a key, they cannot be used in device-independent QKD to distill secret key. And as a first piece of evidence, we checked this bound entangled state example from Vertesi and Brunner, and using the standard well-studied device-independent QKD protocols, you cannot actually generate key with these. And we take this as a first piece of evidence in favor of the conjecture. Okay, so this brings me to the end of my part of the talk. So we looked at upper bounds on CHSH-based device-independent QKD protocols. And then we formulated a revised Paris conjecture that bound-entangled states should be used less for device-independent QPD. And this was it from my point. And Karol Horodecki will now tell you about his work in the second part of this talk. Thanks.
Welcome, everybody. In this second part of the talk, I would like to tell you about recent results obtained in collaboration with Matthias Christandl and Roberto Ferrara that are already published and present on the archive. Regarding outline, I will begin with background and motivation. Then I will show the definitions of device-dependent independent key and give the upper bounds on quantum device-independent key, show the gap for quantum states, and also sufficient condition for quantum states. And in the second part, I will pass the scenario of quantum channels and give upper bounds for quantum channels, giving conclusions and open problems in the end. Regarding motivation, we all know that the upper bounds on device-dependent key we got used to has been studied thoroughly, while the upper bounds on device-independent key not so much. So there is only a handful of papers that you can see here. In what follows, we'll consider quantum adversary, and our goal is to provide upper bounds for quantum states rather than devices and prove the gap between device-dependent and independent key. And we have a provider's perspective, so we ask the following question for a given rho. Does there exist measurements M so that device-independent key of a device M rho can be large? First, what is the device-dependent key? Shortly, the two honest parties share a quantum state, and eavesdropper shares a purification of it, and they can perform measurements. They trust measurements and the dimension of the state. And then the definition is the following formula. This is the asymptotic number of qubits you can obtain divided by a number of n copies you invest, and the supremum is taken over quantum protocols that perform quantum local operations and public communication, and they output epsilon approximate ideal qubits that are in the form of this key for one-time pad, so that you have the uniformly correlated randomness for Alice and Bob, and which is decoupled from Eve. What are the upper bounds? The first is regularized relative entropy of entanglement. So the relative entropy of entanglement is trace rho log rho minus trace rho log sigma. And then if you take infim over separable states of this, you obtain relative entropy of entanglement. And if you regularize, you obtain an upper bound on key. Regarding second bound squash entanglement, it is additive, you don't need regularization. And it is defined as conditional mutual information computed on purification of rho on which you act with lambda on system of E. And the conditional mutual information is described in terms of Von-Neumann entropies as follows. So these are the two upper bounds, obtain these two references. Now we pass to device-independent key. Here the scenario is different. The parties do not trust measurements. They also share a state dimension of which they don't know. Eve is holding purification. They only trust inputs and outputs of the device. And of course, they assume that devices are used only once because otherwise there are attacks on this scenario. So regarding honest implementation, by way of notation, M rho, the pair M rho is a conditional probability distribution obtained by taking trace of rho with measurements. And device-independent key in this case of, in case of ID attacks that we consider, is equal to the rate of dissoluble key obtained by protocol P acting on attacking device n sigma that mimics the honest device up to some vanishing epsilon error, and the error is closeness in trace norm of conditional distributions. And the protocol consists of operations that are from class of classical local operations and public communication. And to summarize this part, we have trivial bounds. So KDI is upper bounded by IID version of it because we restrict the attacks of Eve. And again, the latter is upper bounded by device dependent key for the same reason. And then you have the bounds that I told you before. And as a comment, the first inequality is perhaps equality in general. So our goal is to go beyond the trivial bound and show the gap between KDI and KDD. So as a prelude, I would like to tell you about positive partial transposition, which will be important for the rest of the talk. If you act with transposition only on one subsystem, sometimes you obtain, again, a positive matrix. And this happens also for some entangled states that are called Boundentangled. And some of these states satisfy the condition that they have positive key, and some of them exhibit non-locality. So candidates for the PPT states with positive partial transposition that have positive device-independent key are not excluded, and we focus on these states. And we'll use the partial transposition trick that if you multiply two matrices and take trace, it's equivalent if you multiply them partial transposed and take trace. We'll see that in a minute. So as the main result, there comes the fact that the device-independent key is upper bound by reduced device-dependent. So on left-hand side, we have supreme over measurements of KDI of M rho, which is upper bounded by supreme over measurements of device-dependent key computed on attacking state sigma, where the pair n sigma mimics the statistics of M rho. This is a bit complicated, so we've got a much simpler corollary. For any PPT state, there is the left-hand side is upper bounded of the above, is upper bounded by device-dependent key of rho partially transposed, which is again upper bounded by relative entropy, should be regularization here, of rho partially transposed and squash entanglement of rho partially transposed. So if you're looking for the proof, the corollary is true because simply you can take as an attacking device the device that has partial transposed measurements and partial transposed state. What's important, this result is independent from measurements M. And regarding examples of a gap, we base on the states that were originally found by Lucas Pankowski via genetic algorithms. The basis for the construction you can find in this reference. They are a mixture of separable state and the state containing ideal bit of key with a probability that is asymptotically going to 0 with dimension d. And these states have been first used in the paper by Stefan Baum et al., where it has been shown that device-dependent key of rho d approaches 1 with d going to infinity, and device-dependent key of rho partially transposed is actually going to 0 with d going to infinity. So from that, you immediately see that there is an example for rho 2 to 5. There is a gap between device-independent key and device-dependent key. They are results that I showed you before. And if you take, so you've got a 6 by 6 qubit bipartite state that exhibits the gap. And if you've got more qubits, like 21 per 21 qubits, then device-dependent key goes to 1 and device-independent key goes to 0. And based on that, we have also a sufficient condition if you have a family of, take a family of states that has the following block form. So these are blocks on diagonal, and also here blocks with these parameters alpha, beta, and gamma. Then the following inequality condition upper bound on the Shannon entropy of this distribution. If it's true, it implies the gap between device independent and device dependent key. So in the final part of this talk, I would like to introduce a scenario for channels. So imagine the honest implementation in which we not only focus on the measurements and state, but also on the channel that for which the state is gonna be sent. And this honest implementation can be attacked not only by changing measurements and altering the state, but also altering the channel from lambda to lambda prime. And the attack is successful if the tuple m rho lambda is equal to the tuple n sigma lambda prime, where by this tuple I mean that you first input rho to lambda and then compute the conditional probability distribution with measurements m. And here you first input sigma, state sigma to lambda prime channel, and then compute conditional probability distribution with measurements n. So example of successful attack is that works for channel PBT channels is that you take a channel lambda precomposed with transposition map, then you take original measurements transposed on the B system, and the state you take as it was. And this attack is ideal, it works. So regarding private and DI private channel capacities, I think private quantum capacity we all know. It is the rate of epsilon secret distillable key achieved via n uses of channel lambda and I-way classical communication, where we go with this n to infinity, and the communication can be 0, 1, or 2-way. In the device-independent case, we consider IID version, the IID definition. So we also assume that devices can pass memory, like can keep the history and pass the history from one round to the other, and can use J-way communication between the rounds. So we denote this class by Dij, and the device-independent private capacity of m rho lambda is the following quantity. And in what follows, we'll assume later we'll upper bound it by a restricted version where we do not allow devices to pass the memory between rounds. So we come to the second main result, which is the upper bound on device-independent private capacity. So on the left-hand side, we take supremum not only over rho, but also on measurements. You have a device-independent private capacity of tuple m rho lambda, which is then upper bounded by supremum of m rho of a private capacity achieved by communication from the set maximum of ij, way communication, on the attacking channel lambda prime, when lambda prime comes from the tuple n sigma lambda prime, which is attacking one, that mimics statistics of m rho lambda, and this IDIJ stands for the class where we do not allow this memory passage from round to round. Again, this is complicated, but there is important corollary that the device-independent private capacity of a channel lambda is upper bounded by private two-way private capacity of lambda composed with transposition map. So from that, we take a channel with Choi-Yamilkowski state, of which is the state rho d that I showed you a few slides before. And for this channel, we showed that the two-way private capacity of a channel composed with transposition has almost zero capacity. Capacity goes to 0 with d, growing. So that in turn, the device-independent private capacity goes to 0, while the private two-way private capacity of lambda prime goes to 1. And the latter results have been obtained by Alex Miller, Hermes, and Matthias Christandl before. Here I conclude. We have provided upper bounds for ID device-independent key. What's important, I think these are the first bounds that are independent of measurements. And we exemplify the gap for PBT states and also analogous results for quantum PBT channels. Regarding open problems, the examples that I showed you were high dimensional or like 6 by 6 qubit state or high dimensional channel. So it will be interesting to have analogous results for 2 qubit states and 1 qubit channels, and results in this direction will be shown soon, released soon. It seems that the same strategy, the same approach can be taken in context of other quantum resources, for example, private randomness. So perhaps it can be done. And last but not least, we would like to address the conjecture that Rotem and Felix has put forward in the first part of the talk, namely the question whether PPT states violating Bell inequality can have positive DI key. And with that problem, I'd like to thank you for your attention.